The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
And this relies on the fact that when we talk about enthalpy, or we talk about the heat change of a reaction, this is a state function. And anytime we're talking about a state function, it's independent of path. So essentially, all that we're worried about is the state that we started in. So for example, when we were talking about the oxidation of glucose, the state that we start in are the reactants, so it's glucose plus oxygen, and what we ended up with were 6 moles each of carbon dioxide and water. So we don't care how we get there in terms of making this calculation. All we're interested in is the difference between those two states to think about the overall change in enthalpy. So for example, when we talked about how we could calculate this, one way that we can do it, and we'll look at these numbers even more specifically in a second, is thinking about, instead of going straight down here, which we might not have the numbers available to us to calculate directly, we can think about, well, what happens if instead we break apart this glucose molecule and decompose it into its elements, because using tables in the back of our book, for example, we can figure out what the change in enthalpy is of this reaction here. That doesn't quite get us to where we need to go, though, so then we can think about the enthalpy of formation of 6 carbon dioxide molecules, and then we can go one step further and think about the enthalpy of formation for 6 water molecules. So this is just a roundabout way of going from here to here. Instead, we went up and then down, but because it's a state function, we're absolutely allowed to do this. And to formalize this, we can talk about what's called Hess's law. And Hess's law just tells us that if we have 2 or 3 or any number of chemical reactions that we can add together in order to get the chemical equation that we're actually interested in, we can figure out the change in enthalpy of that reaction that we're interested in just by adding together all of the other enthalpies of reaction for every other reaction that we had to add together in order to get there. So let's take a look at what we're talking about here. So when I just showed you that example graphically, I'm just writing it out more like an equation here, because the nice thing about Hess's law is it allows you to think about chemical reactions kind of as if they're just algebraic expressions. So we can just add all of these different expressions together, and if we're thinking about algebra, we can just think about crossing things out that are in the reactants versus in the products. So if we do this, what we end up getting is the reaction that we're interested in, the oxidation of glucose to form carbon dioxide and water. So let's look pretty carefully at exactly the fact that these all cancel out to give us the reaction I say we get. So for example, we can think about the oxygen molecules. We can cancel out 6 here and 6 here as long as we multiply this whole reaction by 6. Again, we can get rid of those last 3 oxygen molecules there. Similarly, we can cross out our 6 hydrogens from the products with 6 molecular hydrogens from the reactants. And then the last thing we can cancel out are our carbon atoms. We have 6 in the products, and we have 6 in the reactants here. So you'll see that the only things that are not canceled out is what's left in our bottom reaction. So we can go ahead and just add up all of these different reaction enthalpies. In the first case, what we're going to have is an enthalpy of 1260, and that's in kilojoules per mole of oxygen, or excuse me, per mole of glucose. And the reason that this is positive is because it's essentially the reverse reaction of the change in enthalpy of formation. So it's going to be a positive number there. We add to that the enthalpy for this reaction here, which is negative 393.5, but we need to remember to multiply that by 6 because we're actually adding together 6 of those individual reactions. And lastly, we also add together 6 of this final reaction here, which has an enthalpy change of negative 285.8. So if we go ahead and just add up all of our individual enthalpy changes, what we're going to end up with for our entire reaction here is a change in enthalpy of negative 2816, and that's kilojoules per mole of glucose. Does anyone remember from Wednesday's class, does this match what we had seen experimentally? Yeah, so this is the exact number that we calculated when we used heats of formation, and it's also the exact number that's seen in terms of experimental.